Hi, welcome to lecture 11. In this lecture, we will continue with our development of entropy method, and we will take a slight detour because there are some very interesting formulae that we need to proceed to apply entropy method to general random variables. In the last week, we saw how entropy method applies to binary random variables as well as Gaussian random variables, and now we will proceed and extend the same bounds to general random variables. Towards that, we need some variational formula for KL divergence, and it is not immediately clear what this formulae do, but in this class we will just collect these formulae, and then in the next lecture we will move forward to apply this formulae to obtain our desired bounds. So we'll start with a classic formula known as Gibbs variational principle, which is a variational formula for the log moment generating function. Last week we saw that we saw this 2 weeks back, I think. We saw this beautiful formula for log moment generating function, which relates log moment generating function to the divergence of the tilted measure from P, where this tilted measure is this exponentially tilted measure defined this way. Okay, so this measure has a density given by e to the power t z by its expected value with respect to P. This quantity can be related to this quantity here, this ratio can be related, this divergence can be related to the entropy of e to the power tz, and that therefore whenever we can bound entropy of e to the power tz, that can yield a bound on the log moment generating function. This is what we called entropy method, what we have been calling entropy method. And in this lecture, we will present another variational formula for this log moment generating function. In fact, what we present in this lecture is perhaps about 100 years or 200 years older than this formula. So let me present that formula. So we will show that the log moment generating function for a zero mean random variable. For simplicity, we'll have a zero mean random variable at lambda. Maybe I should just write it this way. So the log moment generating function e to the power lambda z minus expected value of z, and every expectation here with respect to P can be expressed as sup over all distributions Q that are absolutely continuous with respect to P. Expected value is lambda here of z under Q minus expected value of z under P. This is because you've done the subtraction, minus divergence between Q and P. Okay, so if you take supremum of this quantity over all Q that have density with respect to P, that are absolutely continuous with respect to P, that is equal to the log moment generating function. So this is the formula we will derive. So this formula here is there are various ways to see it. One interesting way is that one thing to see here is that we were taking expectation of sort of a complicated function. This is e to the power, sorry about this. This is a complicated function of the random variable, but what we have here is just linear expectation. So somehow this linearizes this whole quantity. Okay, and it's a very famous formula which gives an alternative expression for the log moment generating function. Later, we will develop the transportation method which exploits this formula to derive concentration bound. In this class, we'll just give a proof for this formula. So proof. So we once again consider that exponential tilting of P. So let QZ be QZ absolutely continuous with respect to P. So QZ, which has a density with respect to P, be given by, so we just have to define the density. As before, this guy has density e to the power z minus, well, let's just prove it for e to the power z first, by expected value e to the power z. Okay, so look at this guy, and what we notice is that the distance, the divergence between this guy and the divergence between q and this guy must be greater than or equal to 0. That's what we check. That's what we notice. And to talk about this divergence, we first must ensure that this qz also has divergence with respect to q also has density with respect to qz, and that's something that can be verified. Okay, so this guy here, what is this divergence? This divergence can be written as expected value over qz of the density of q with respect to qz log density of q with respect to qz. And this can be written as the expected value over p now. This is because this qz has a density with respect to p. Density of qz with respect to p times this log density of q with respect to qz. So this guy here is expected value over p. This is how redound-Nikodym derivative work, but you can verify this for discrete case easily. Again, I'm leaving that as an exercise. This is just dq by dp, the density of q with respect to p, and log of dq by dqz. So I'll write it again as dq by dp times 1 by dqz by dp. Okay, that this is also true. This is almost surely these things are equal to this. So if you are very confused about what's going on here, what is this voodoo math, you just write it as summation for discrete case, and then you will see how this is a ratio of two PMFs, and you can divide and multiply with you can bring this in and divide and multiply with these two densities. Okay. So that's how it is working, or just the ratio of PMFs. That's the easy way to see it, or ratio of densities when everything has density with respect to the Lebesgue measure. So everything is a continuous random variable. But here we are talking about densities with respect to some other measures. So I'm using some technical result in the middle of all this, but they are all believable results. So that gives you expected value with respect to p log of this plus expected value with respect to q now log of, because we have a dq by, maybe I'll go slow here. So this is p dq by dp log, so log of dqz by this, what is this density? Well, by our design, this is e to the power z by expected value with respect to p e to the power z. Alright, so this first term here you can recognize as the divergence between q and p. So that's what this first term is. And this, now this I'll divide into two parts. Log of a constant, expected value of some constant. This is just a, maybe this one here, the second term here. You can recognize it as expected value with respect to q, because you have a redound-Nikodym derivative here. This allows you to convert expectation with respect to p to expectation with respect to q. Log of e to the power z by this guy. So this is minus expected value with respect to q of z, and then plus log of expected value with respect to p e to the power z. Okay, that's the inequality we get. We get that this whole thing here is non-negative. And so what that implies is that the log of log moment generating function exceeds EQZ minus DQP for every Q that has density with respect to P. But in fact, we also know the condition for equality. The condition for equality is when this Q is equal to this tilted measure here. Okay, so with equality, if and only if, because divergence is non-negative unless the two distributions are equal. So if and only if Q equals to QZ. Okay, therefore not only this inequality holds, but there is a distribution for which there is equality, and therefore log expected value over P of e to the power Z is equal to max over all Q that are absolutely continuous with respect to P. Expected value with respect to Q of Z minus DQP. Okay, so you may wonder what happened to the centering part. Well, it comes for free. So this centering part, replace Z by this guy, Z by the centered version, and then you will get, so replace Z with this guy. So you get expected value over P e to the power Z minus this is equal to max over Q expected value of Z under Q minus expected value of Z under P minus DQP. Okay, that's the form we had seen in the claim. Okay, so that's roughly the proof of this very classic formula and very useful formula. It has various names: Laplace integration formula, Gibbs variational principle, Tonsker-Wardha variational principle. All these things are related to this formula itself. And I wrote soup here, but we saw that we have a max actually. This is the measure which attains it with equality. Just if you want to visualize this proof, all this proof is saying is, you look at, as you change these different random variables, this random variable Z, you can define a measure which passes through P for a constant Z, for Z equal to 0. This is equal to the measure P. So you have a P and you for different Z get something like this. This is your QZ. Okay, and Q of 0 equals to P. And there is some measure Q, and we look at the distance of this from Q. And we claim that for any Q, this distance is non-negative. Yeah, of course. And that's what this inequality is. And it is equal if this Q lies on somewhere here. So for that particular Q, these two things coincide and the measure is 0. And then the distance is 0. That's what this inequality says. Okay, so that's the Gibbs variational principle. Now, in fact, if you look at the title of this section, I said I'll prove the Gibbs variational principle formula, and it's sometimes called the Gibbs variational principle, and a variational formula for KL divergence, the Kullback-Leibler divergence. So, as perhaps now you can guess, we can invert this formula by taking divergence to this side. So, the formula we get is, we can manipulate the form above to get a variational formula for KL divergence. So indeed, we have shown that for every Q, that has density with respect to P, the log moment generating function so this is for every q and this is for every random variable z, and every z such that expected value e to the power z is finite. Log moment generating function is equal to, not just equal to, it exceeds expected value with respect to q of z minus dqp. So that is, this divergence between q and p exceeds the expected value under q of this random variable z minus log expected value over p of z. And this holds for every z. So therefore this holds for sup over all z such that expected value under p of e to the power z is finite. In fact, if this thing is infinite, then you have infinity here and minus log infinity is minus infinity. So this holds automatically. But for sanity check, we just put it to be finite. Okay, so maybe, I don't know, this maybe you like this one. So because when this is infinite, the bound holds trivially. Okay, so this is greater than equal to this. So we have this bound. Now this bound holds, but can we find a z for which this for equality holds, and that z exists. On the other hand, for z equal to the Radon-Nikodym derivative. Note that this Radon-Nikodym derivative is it's the density, but that's also a random variable because it's a function of the underlying probability space. So this is a random variable. For this random variable, let's compute this right side. Expected value over q of z minus log let's take a log here, log of the guy, expected value e to the power z. This guy equals to expected value under q of log dq by dp make some space. So this guy equals to expected value under q of log of dq by dp minus log of expected value under p of e to the power z, which is just dq by dp. Now if you look at the second term here, this guy is 1, so this second term here is 0 because this expectation is 1. This just changes the measure. It's just expected value of 1 with respect to q. And this guy here is another term disguising our Kullback-Leibler divergence. We have seen this equivalent expression before. Yeah, so once again, remember that if you want to switch from measure q to p, you only have to multiply with this density. So you have this is equal to dqp. Minus 0. Okay, so there is indeed a random variable for which we get dqp for the right side here. So in fact, this inequality which holds, it actually holds with equality because there's something here for which this is equal to this. So to conclude, what we have obtained is this another alternative form of the Gibbs variational principle. I think it's just an alternative form, but maybe you don't want to call it that. So this is max over all random variable z Note that this random variable z actually has e to the power expected value of z under p as 1. So this is finite for sure. So if you want, you can write it as max over all random variables z, such that expected value of this is finite. But as I said, this can be drawn. Expected value under q of the z, so the new measure, minus the correction due to Logmoment generating function. Okay, so this is we converted Gibbs variational principle into a sort of a variational formula for divergence. Okay, so this is the first variational formula for divergence that we saw. Right, this is what I want to say in the first part of this lecture. Now moving to the next part of this lecture, we will present another slightly different variational formula, again for KL divergence, and this one uses something called Bregman divergence. So another variational formula for KL divergence. Okay, and this uses a thing called Bregman divergence. All right. So what is this Bregman divergence based formula? In fact, you should ask me what is this Bregman divergence. So let me start by defining Bregman divergence. So given a convex function, given a convex and differentiable function, f, so on R, but let's say just an interval of R, where is an interval so just I just switched context very quickly. So this divergence, this variational formulae, firstly you may wonder why they call variational formulae. I never described that, and that's a very rich story. But one way to think of this formula is it's a series of bounds, and any of these bounds is a lower bound for divergence, but this collection of bounds is tight because there's one which meets it with equality. And the first formula that we presented is sort of a family of lower bounds for KL divergence. What I'm presenting now is a family of upper bounds for KL divergence. Okay, that's the second variational formula we are presenting, and it uses a different idea. It uses this idea of Bregman divergence. So you're given this convex function f, convex and differentiable function f. For this such a function, we can define the Bregman divergence of f, and it requires 2 points from x to y. Okay, here x comma y are in this interval. So Bregman divergence from x to y. This is the is defined as we can use a notation, but since we never go back to this one, I will not give a notation. It's fx minus x to y. So you go from x to y, fy minus fx minus f prime x into y minus x. So can someone recognize what this quantity is? And you have to keep in mind that f is a convex function, right? So since f is a convex function, it looks something like this. We took 2 points, x and y, And so this is, let's say, x, and this is y. And we looked at the tangent at x, f prime x. This is here in this direction. So that's the direction f prime x. And we took a step equal to x minus y in this direction. That will get you somewhere here. So that's my y. So this point here, when you move, is what is the value of this point? It's f prime x into y minus x. That's the value of this point. Okay. So, and what about this difference here? So this is fy, this is fx, and what we are looking for is how much larger is fx in comparison to fy. So this quantity here is this distance, and it's always non-negative because the function is convex. Okay. So now we state a result which is a generalization of a well-known result that I'll tell you about later. So here is another variational formula. So we'll just call it a lemma. So no, this is the Jensens Gap variational formula. So for a random variable x, consider expected value of f of x. So once again, by the way, f is a convex differentiable function. Maybe f from I to r as above is convex differentiable. So now we consider the Jensens gap, what I'm calling Jensens gap. So remember that the expected value of fx minus f of expected value of x. By Jensens inequality, this quantity is non-negative. Okay, and what we are claiming is actually this guy. We'll write a variational formula for this guy. It's in the infimum over all a in the domain of f. So all the best constant a that you can choose. Expected value of f of x minus f of a minus f prime a into x minus a. In fact, I've written it as infimum, but you see that when you substitute a equals to expected value of x, so this becomes fx minus f of expected value of x, and this guy is minus f prime a and something here. And so when you take linearity of expectation, this expected value becomes 0. So in fact, this can be attained by a equals to expected value of x. So in fact, this is a min. Okay. This is a min if expected value of x belongs to this interval, but that is true because x is a random variable on this I. Only then this can make sense, and therefore expected value of x is also inside this I. Okay, right. So this is this nice formula that we were after. This is the second. Yeah. So we haven't still talked about how this is a formula, variational formula for divergence. But before we do that, one remark. So let's choose a very simple convex function. Okay, consider fx equals to x square. Perhaps the first convex function one can think of. Okay, in that case, what is this formula saying? It's saying that expected value of x square minus the mean. So expected value of x square minus expected value of x square. Okay, so this is basically, we recognize this as variance of x, which is expected value of x minus expected value of x square. this guy is equal to minimum over all a expected value of x square minus a square minus 2a, that's the derivative, into x minus a. And if you look at this formula carefully, so you get plus 2a square minus 2ax. This is nothing but x minus a square. So this brings out the familiar formula. Okay. Yeah, the familiar formula. It says that expected value minimizes the mean squared error, MSE. This is the mean squared error, and the constant which minimizes this is expected value. That's something you have seen. Perhaps you know about it. Otherwise, you can. Here is a proof. Okay, by applying this formula, which we haven't proved yet. So that's what we have seen. Now, an interesting. So what happens when you look at the other convex function that we have been using in this course? So here is the corollary that we were after. By applying the variational formula for Jensens Gap to, so now we apply it to the other convex function, x log x. Remember, just like we extended Afrenstein to entropy method by replacing this x square with x log x, we do the same thing here. So we apply this here, we get expected value of x log x. Okay. Minus expected value of x log expected value of x. This guy here is equal to minimum over all a, constant a, expected value of, let's see, fx minus fa, fx minus fa minus f prime a. So what is f prime a? That's 1 plus log a into x minus a. This is the same as minimum over a expected value of x log. So this a log a cancels with this a log a here, and so you are left with x minus a plus x log a minus x log a. So you get this, perhaps this, minus x minus. So what we have, if you see this guy there, then you recognize it perhaps as the entropy. So we have shown that entropy of x is equal to minimum over a expected value of x log x by a. Let's just, because we're talking about entropy, we take non-negative random variables here. And this, just to be sure, I clarify that we choose I to be 0 to infinity here. In fact, we should rule out 0 also, no problem. Minus x minus. Okay, so this is the formula, variational formula for entropy that will be very useful for us. And in fact, as we know that when x greater than 0 is given by, so let's say when x is equal to dq by dp for some q that is absolutely continuous with respect to p, entropy of X is equal to divergence between Q and P. And then this guy we are saying is equal to min over A greater than 0, expected value of, this expectation is with respect to P here, so dq by dp log dq by dp minus log A minus dq by dp minus A. So this guy here is equal to this guy here, min over A greater than 0, expected value over P I think that's okay. Yeah. So this is another formula for divergence. And now this time we have a min here instead of max. Okay. So it's better to remember this formula in terms of entropy. So the important point is you have a min here instead of max. This is the second formula for variational formula for divergence that we wanted. Alright, so this is all corollary of this Jensens Gap variational formula, which is in terms of this Bregman divergence of f from A to x. Okay. So how do we show this formula? This is the proof of the Jensens Gap variational formula. I'm making this name up, it's not a standard name, but you know why I'm calling it that. Alright, so for Jensens Gap variational formula, how do we show this? So since this is a generalization of this proof of the fact that expected value minimizes the mean square error, we'll follow a similar proof. We will take the difference between the Jensens gap, this right side here. That's how you prove this for this case. So this right side here, this expression here, this one, and for A equal to expected value of X. So fx minus fa minus f prime A x minus A. That's something we would like to claim exceeds the other thing. Fx minus f of expected value of x, f prime expected value of x into x minus expected value of x. Would like to claim that this whole thing is non-negative. So let's just take expectation outside, and we see that fx cancels, so you get f of expected value of x minus f of A, and now minus f prime A x minus A. And now if you see this expected value here is 0, so that's all. Okay? Because this is a constant, so these two match. So this is this. Okay, but this is exactly equal to f of expected value of x minus f of A minus f prime A expected value of x minus A. What is that? That is the Bregman divergence of f from A to expected value of x. And this guy is non-negative. Okay. And of course, you can have equality here by setting A equal to expected value of x. And that's the proof. This is always non-negative, and there's equality when A equals set to expected value of x. Alright. So this is the proof of Jensens Gap variation formula. And we can apply different functions here and get all these different variation formulas. So two takeaways from this lecture. Actually, there are 3 takeaways, but I need not overplay the first one because we'll spend a lot of time on that one. The first one, the main one, perhaps in the long term, is this Gibbs variational formula here. It gives you a new formula for log moment generating function. Okay, we'll come back to this later. But for our immediate use, we want to recall 2 variational formulae. One for this divergence, it's the max of expected value of max over all random variables z, expected value of z under q, minus the log moment generating function with respect to p. So log of expected value with respect to p of e to the power z. Okay, that's divergence. And second is this Gibbs variational formula. Or second is this variational formula for this Jensens Gap thing that I derived. But instead of that particular formula, what we can remember is its consequence, which gives a nice formula, variational formula for entropy, which is similar to divergence. That entropy of x is equal to min of all non-negative a, expected value of x log x minus log a minus x minus a. Okay, so in fact, our motivation for covering this variational formula or both this variational formula at this point was so that we could derive this particular formula for entropy. And in the next lecture, we will apply this formula to obtain a sort of a log-Sobolev inequality, slightly different log-Sobolev inequality. Till now, we have seen the binary log-Sobolev inequality and the Gaussian log-Sobolev inequality as its consequence. And now we will use this variational formula for entropy to derive the so-called modified log-Sobolev inequality, which will allow us to extend the bounds that we saw in the concentration bounds that we saw in the previous lecture for uniform random variables over the Boolean hypercube and for Gaussian random variables to arbitrary random variables. Okay, that's what we'll do in the next class. Just remember this formula. See you in the next lecture.